take analysis of beams subjected to a train of moving loads. Already I have given how the train of moving loads will look like. So it will be a train of concentrated loads in this fashion, either moving from left to right or right to left, from one end to the other end on a simply supported beam like this. So due to this movement, there will be maximum shear force developed in the ends of the beams, as well as at any section, the maximum shear force and bending moment at any section, and absolute maximum shear and bending moment for the design of beams. All these four quantities we have to determine. So first let us take a train of concentrated loads in this fashion. Four concentrated loads, I will take it. There may be any number of concentrated loads. We will take up four concentrated loads which are kept at fixed distance, always fixed distance apart. We say this distance x1, x2, x3, the four loads for W1, W2, W3, and the V loads 1, 2, 3, 4 like this. So let the CG of these V loads be at a distance x bar from the first wheel load. So that also we need the CG of wheel loads. That also you can determine. Whenever a train of concentrated load is given, so you have to find the CG of the wheel load, location of the CG of wheel load from one end. Then also you have to identify the two concentrated loads which are on either side of this centered of wheel loads. So the distance of these two wheels from either side of this, that also you have to locate it. So I hope you know how to find out the CG. You take moment load, one end of the wheel load. Say from W1 you want to determine the location of the CG of wheel loads. You take the moment of all wheel loads about that W1. So that is W2 into x1, W3 into x1 plus x2, and W4 into x1 plus x2 plus x3 divided by the total load. W1 plus W2 plus W3 plus W4. That will give you this x bar. This x bar you can compute by taking moment about W1, that is W2 x1 plus W3 into x1 plus x2 and plus W4 4 into x1 plus x2 plus x3. This entire sum you can divide by the sigma W, that is W1 plus W2 plus W3 plus W4. That will give you the value of x bar. That you have to locate it, and then from that CG, the two nearest wheel loads, W3 and W4, one on left side, other on right side. That load distance also you have to determine. En, I will call the location of the left side nearest wheel load. Er, I will call the location of the right side nearest wheel load from that center of wheel loads. So this will help you in finding out the absolute maximum bending moment. You have to place this, either this wheel load W3 at a distance is equal to L by 2, where L is the span of the beam, L by 2 minus EL by 2 from the center of span. That symmetrically you have to place that wheel load about that center of span. Or this also on the right side, we also have to place it to find out the maximum and the absolute maximum bending moment. That's why in the beginning itself, you have to just find out all these things, that is CG of the wheel loads and its location from one end. So let AB will be on which this strain of concentrated load moves, and let C be any section in the beam at a distance A from left end and B from right end. And let the load move from left to right. So that you can say, consider a train of concentrated loads W1, W2, W3 and W4 at fixed spacing, x1, x2, x3, x4, moving or rolling on a beam AB of span N from left to right. Let C be any section in the beam at a distance A and B from left and right end respectively, as in figure. Let X bar be the location of CG of wheel loads from left extreme load W1. So this W1 is called left extreme load. This is left extreme load. This is the right extreme load. So let X bar be the location of CG of these wheel loads from the left extreme load W1, and EL and ER be the location of wheel nearest wheel loads, that is W3 and W4 from CG of wheel loads on either side. That EL and ER be the location of nearest wheel loads, that is W3 and W4 from CG of the wheel loads on either side, on left side as well as right side. This much information you should know whenever you have been given a train of concentrated loads. In UDL, whenever the moving load is or rolling load is UDL, then all these exercises you need not do. But here you have to do these exercises which will help you. So next, as we have to determine during analysis, the following. That is, as you have seen in case of UDL, the same things you have to determine. The first one, maximum reaction at the two ends, supports A and B, that is RA and RB, maximum RA and RB. You have to determine that. The first thing during analysis you have to determine. Then maximum shear force and anti-moment at any section C in the beam. So that whatever I have located here, any section at a distance A and B from left and right hand, at that particular point, you have to find maximum shear force and maximum bending moment. In the case of maximum shear force, you have two varieties of shear force, that's negative as well as positive, that you know. So that maximum negative shear and maximum positive shear, both you have to determine, as well as maximum bending moment at any section, that is this point C, you have to evaluate during the analysis. And the third one, maximum bending moment at section C, that also you have to determine, shear force and bending moment. Then lastly, you have to find out what is known as absolute maximum shear force and bending moment in B. This is also called as design shear force and bending moment of the beam. Both you have to evaluate. So these four quantities you have to determine during the analysis of the beam, whenever it is subjected to a rolling load of train of rolling loads due to train of concentrated loads. So this is what you have to determine. Now we will take up one by one. First, to find maximum support reactions, maximum RA and RB, that we will evaluate. That's the first thing. So as I was telling in the case of UDL, first you have to ascertain what should be the position, how this wheel load has to be placed on the beam in order to get the maximum value of support reaction. That you have to ascertain. That's the very first exercise you have to make. So as we have seen in the UDL case, here also to get maximum RA and RB, all these wheel loads has to occupy the span with the extreme right load, extreme left load occupying the position A. That will be the critical position of these wheels to get maximum RA. The position has to be like this. Position of wheel loads, it has to be like this. The maximum or the left extreme load has to be placed at A, that is W1, has to be placed at A in order to get maximum or A. So first that you can say here, to get maximum or A and or B, the first or initial position, of the wheel loads should be as in figure. So to get maximum RA, the extreme left wheel load has to be placed at A. Whereas in case of finding maximum RB, we have to place the right extreme wheel load on B. That is W4, then W3, then W2, W1, like this, you have to place. To start with, initially. So we are adopting a sort of trial and error method in order to find maximum RA. Always first trial, that is first position of the wheel load, you have to place it like that. Whereas in UDL, what we were doing, we were placing tail of UDL here, head of UDL here. Whereas here, the left extreme wheel load we are placing at A, and right extreme wheel load we are placing at B. It is similar, whatever we have done there, here also we will do. There, the tail and head portion of that UDL will be the left extreme and right extreme of the train of concentrated load. That you have to follow. Then you have to use the influence line diagram for RA and RB, and for this first position of the wheel load, using that in the influence line diagram, you have to evaluate RA and RB value by determining the ordinates by similar triangles. That is the first exercise you have to make, or first calculation you have to make in order to find RA and RB. Then you have to allow the wheel loads to move from right to left and left to right, one by one, for these two cases. So next you have to allow W1 to move and bring W2 at A. Here W4 you move on the right side and bring W3 on B. Again, take the influence line diagram, get the ordinates, calculate RA and RB. You compare the two values, whatever you got, new value of RA and RB with the previous value of RA and RB. If it is less, then you can say the previous position is the critical position of the wheel load to get maximum RA or RB. Otherwise, you continue that process until all other wheel loads will occupy that. So it's a sort of trial and error method I told you. Only calculation you have to make is the first position of the wheel load. First trial you should know that allow them to move either towards right or towards left and bring other wheel loads to occupy that position and use ILD, get the ordinates. That while getting the ordinates you should not do any mistake. By similar triangles you get the ordinates at various points, multiply those ordinates by the intensity of the corresponding loads, sum up, you will get the value of RA and RB, and go on comparing that RA and RB for each trials until you get maximum RA or RB. That's all the exercise you have to make. That's the only thing. As in figure. So this is first position or first position or trial 1. It is called trial 1. First position of these wheel loads for RA. Here this is first position or initial position of wheel loads for RB. This you should know as in figure, then use the influence line diagram for RA and RB to get the value of RA and RB for this position of this. So the influence line diagram for RA will look like that. This is ILD for RA. At this point, W1, the ordinate will be 1, and at this W2, you have to work out this ordinate. How to work out? That is 1 divided by L. This is the distance here. 1 divided by L. This you are getting for a length of this 1 ordinate you will get for a length of L, and for this length you can work out. This is nothing but L minus x1. So for that L minus x1, what is the value you find out? Similarly, and here L minus x2 ordinate, you determine 1 by L. First, 1 divided by L value, you keep it, then simply multiply by the distances of other loads from right extreme. This you find multiply by L minus x1, this you multiply by L minus x1 plus x2, the other one L minus x1 plus x2 plus x3. You will get these ordinates. So this is y1, y2, y3, y4. Then w1 into y1 plus w2 into y2 plus w3 y3 plus w4 y4 will be your RA for trial 1. Right? So then RA for trial 1 we can work out as W1, Y1, W2, Y2 plus W3, Y3 plus W4, Y4. Next, you can draw the influence line diagram for RB that will look like this. For this position of influence line diagram, ILD for RB, for this RB, you again find out the ordinates under this W4, W3, W2, W1. You can call this again as Y1, Y2, Y3, Y4. This is for the Y4, like that. So you work out this RA on similar line, similar triangle. You first find out 1 by n, that value you keep it, that 1 by n, that value multiply by this. This is again L minus x4. There it was L minus x1, here it is L minus x4. Then L minus x4 plus x3. Then L minus x4 plus x3 plus x2. Like that, you can find out that particular ordinate. This is the only exercise which you have to make without any mistake. That's all, first try. Then you allow one by one to move. Go on repeating this process until you get maximum value of RA. You have to stop at that stage. That's all for determining the maximum reaction in the beam, either left or right support.
So that is RB, right, sir?
So this is RB first trial. It is also W1, Y1 plus W2, Y2, W3. I am using same symbol Y1, Y2 and all, but it is for this sketch. You have to take it. So this is what you have to do. Then next, after arriving at that, repeat. This is step 1. This is, you call it as step 1, then step 2. Repeat. Repeat step 1 by allowing by bringing, so allowing, we say by bringing the next immediate V load on A or B. Right?
Yes, sir.
So next immediate V load, here it is W2. Here next immediate V load is W3. That you keep it. Again, you repeat this exercise. You measure the ordinate for that position. So the other V load will move out of the beam span. So for others, you work out this RA and RB. So then last step 3, find the maximum RA value of RA or RB from the above trials. You stop your work whenever for which the trial for which the value becomes less. You can stop at that stage. And this absolute maximum shear force, here itself we can determine absolute maximum shear force will be the maximum value of either RA or RB. Whichever is maximum in this RA or B, that we call it as the absolute maximum shear force or design shear force for the beam. That another thing you have to remember. That also you can note down the absolute shear force in beam will be maximum of RA or RB. So that you can determine here itself, absolute maximum shear. So this is about the determination of maximum end support reaction as well as absolute maximum shear force in the beam. So the exercise what you have to do is very simple arithmetic calculation, nothing other than that. Only you have to determine correctly the value of the ordinates. knowing this standard influence line diagram. This you are not supposed to forget it. In all your stress analysis, this beam analysis, as well as here, rolling load analysis. The standard influence line diagram for reaction and suppose shear force and bending moment at any point, and you have to remember whatever we have developed earlier. That you are not supposed to forget it. So next we will take up the second one. That is how to find maximum shear force and bending moment at any section of the beam. Here it is only trial and error process, nothing other than that. So we have another shortcut method, but it will not be always useful, because whenever this length of this UDA concentrated loads will be more. When beam is this thing, one of the wheel loads, if it goes out of this span, then it is cannot be used, that shortcut method. As long as this is shorter than this span, then you can use it, because generally the wheel loads will be longer in length. We have tried enough concentrated wheel loads attached using either our highway girders, highway bridge girders, or railway bridge girders. It will be longer than the span, given particular span. So that limitation is there. So I will prefer only the use of this trial and error method rather than that shortcut procedure. The shortcut procedure, you can just don't keep it in mind. Just go on doing this, because hardly in the examination also they will give 3 or 4 loads maximum, not more than that. You should be fast in doing this arithmetic calculation. And not all these 4 they will ask in the problem, only 2 they will ask. Either maximum reaction and absolute maximum this, or this maximum shear force and bending moment at any section, or this. Only 2 they will ask, so that it won't be time consuming. You can finish it well within half an hour. So just to stick on to trial and error process. So next we will take up the evaluation of maximum bending moment and shear force at any section C in the beam. That we will do. Again, the procedure is similar to what we have seen in the reaction. First, you have to place the wheel load. That is trial 1. So you have to place that wheel load in the first position, then go on allowing it to move one by one, and do that calculation for VC, that maximum shear force at C, either negative shear or positive shear, and go on repeating it for the next position until you will get the maximum value. That's all. The same process. It is a very simple procedure is very simple. Calculation also, it is very simple. I told you, first you arrive at one value, that is 1 divided by L, as I have told here. That value you just simply multiply by the distance of other ordinates where you have to determine. That's a very simple calculation. That calculation you have to do fast. So you can to find maximum shear force. We will take first maximum shear force at C. Both we see negative shear and positive shear. So here, as you hear, the first trial is you have the beam, you have the section C, the distances A and B, the total length is L. So first position here, first it is to get maximum VC negative, that is negative shear force. First we will take. The first trial is we have to place the extreme right wheel load at C, that is W4. We have to place it here. Then other fixed spacing, because these are all at fixed spacing, so you have to place other wheel loads. Suppose only 3 loads are possible here. Suppose if these distances are such that, suppose if this is say 9 meters or 8 meters. So this distance 4 meters, 2 meters, 3 meters. 4 plus 2 plus 3 becomes 9. So this distance is 8. So in that case, first I have to place right extreme wheel load here. One wheel definitely goes out. So that's why I told you that limitation is that to use that shortcut criteria. So we have to adopt this trial and error process only. That's why I told you, you stick on to that process only. So you just first place that right extreme wheel load at this section, then you arrange the other wheel loads which are possible. Right? That only you have to arrange it. That W3, W2 and this W1 may go out of span or it may be within the span itself. So that depending upon that spacing, that you have to make sure. Right? When it goes out, don't bother. Whatever is wheel loads which are possible to occupy that, let you keep it. But as a general rule, we say all wheel loads should be this kind. But given section is itself is very, very small from one end and it is lesser than that wheel load length, then we can't help. Some wheel loads definitely it will go out of the span, that you don't have to bother. But only thing is first wheel load you have to place, that is right extreme load, you have to place at C and you arrange other wheel loads. Then you allow one by one to move. Now until you have to exhaust all the wheel loads on this span, then you can stop. Right? When all wheel loads comes on this span, you can stop it and calculate for that. So that's the first. This is your trial 1, that is position of wheel loads. Wheel loads for BC negative. You have to place wheel load like this. And to get maximum positive shear at C, right? You have to, it's the other way, as you have seen in UDL, shorter than span. So you have to place this left extreme wheel load first at W1, then others. You have to arrange like this, W3, W4. That same rule. If all the wheel loads comes, well and good. Otherwise, don't bother. So you have to place it like that. So always, so to get maximum we see the extreme right wheel has to be placed at C. There the tail, your head we were, no, tail we were placing. So here also do the same. Now head we are placing. This is head, this is tail. Right? Here we have to place tail, and here we have to place head. Or if you number this W1, W2, you can reverse it. You can call in that particular fashion. Here I am using that notation. This I am calling it as left extreme, head extreme. Here you have to place the left extreme. Here left extreme. Here we have to place head extreme. Then you have to allow it to move this way and this way one by one. Whereas there it is reverse. You can see it was moving in that same direction. Here it is not so. From the first trial. So that you have to be careful. Remember this. So the extreme right wheel load has to be placed at C to get maximum VC bar, and for this, as in figure. So then using ILD, calculate DC negative. So the ILD will be like this. This is the standard ILD. This is ILD for BC. So this is A by L, this is B by L, where A is this distance, B is this distance. So this is positive shear, this is negative shear. For this particular position, you have to get the ordinate here, Y4, then Y3, Y2, Y1 for negative. Then you will load now and calculate VC bar negative. Then you will next field to occupy. Again calculate it. Whichever gives you maximum, that will be your VC naught. So using ILD, calculate VC bar and repeat this or other field loads. Other field loads are to take point C, one by one, until we get maximum VC. Then B to get maximum VC positive. To get this, the position, you have to place the extreme left wheel load. So place extreme left wheel load at C as in figure. This position for BC initial position as in figure, and using IID calculate BC positive. So at this position you work out the ordinates y1, y2, y3, y4. Calculate each part. That is W1, Y1 plus W2. This as before, you get YC positive for first stage. Then we allow you to move for the second position, calculate it, third position, calculate it if it required, until you get maximum value. That's all. That is how to find maximum shear force, negative shear force, as well as positive shear force at a section. This is again nothing much here to remember. Only the position you have to remember. Which should be either left extreme load or right extreme load. Keep it at that particular section. Allow it to move either left or right until you arrive at the value. Right? Next we will take up the maximum bending moment at any section. So here, slight change is there. As you have seen in UDL also, we have to, you have seen the criteria is the average load on left side and average load on right side, they should be equal. Or in other words, the load should divide the section should divide the load in same ratio as it divides the span. That is, in other words, the average load on left side should be equal to average load on right side. Both are same. That same criteria we use here also to get maximum bending moment, and to how to place the load we use that criteria. So next, to find maximum bending moment at C. Right? So the position of wheel loads, to get maximum bending moment at C should be such that the average load should be such that the average load on left and right of section should be same. Or in other words, the section should divide the load as well as the span in same ratio. Or the section should divide the load and span in same ratio. Both are one and the same. So here, this is easier for computation. So this you have to do with some preliminary exercise in order to arrive at that position of the field loads. So this again a trial and error process. First, as you have seen in maximum shear force, this you can just allow the wheel load and place it, allow the wheel load to move from left to right, and first place the extreme right wheel load at C. Right? So when I place this extreme wheel load at right wheel load at C, so we assume one thing, this wheel load W4 is on the right side. It is about to move, or it is on the right side itself. Always the value of either shear force or bending moment, it corresponds to right side value. So whenever I say a load, some load on the section, that means for calculation purpose, that load has to belong to right side. Right? So you find out the average load for the first trial. Whatever average load is there on right side and left side, you can calculate it. So average load on the right side will be W4, I told you. So that is whatever wheel load you place it, that you assume it to be on the right side. So that W4 divided by B, that is your average wheel load on right side. And on left side, so this is, if it is not there, you take only the other two wheel loads divided by A. You just find out whether WL is less than or greater than WR. That you keep it. In the form of table, you can do the calculation. Next, you bring the next wheel load. So next wheel load, when you bring it, the average load on the right side will be W3 plus W4 divided by B. Then this will come here. So you take all other wheel loads on the left side, that divided by A. So you find out whether WL is again same thing, less than or greater than WR. When it changes, suppose earlier WL is less than WR, in second trial WL is greater than WR. That means the average wheel load here and average wheel load here, that is passing through zero value. That means it is equal at some point in between. Yes. So we assume if whatever wheel load, in that particular case, whatever it happens, at that particular case, you take it, the previous case only. That you take it for that position. Right? You take the standard bending moment at that particular section, calculate value of X. Then you allow wheel load to move from right to left, repeat the process. For these two cases, generally it will be equal if these sections exactly bisect, otherwise there may be slight variation. Generally, it will, if B is greater than A, in this particular case generally gives you maximum bending moment. Otherwise, better do both the calculations, you will never miss anything. So repeat that by allowing this second case, and out of these two, whichever gives you maximum bending moment, that you say. That's all. Only one extra criteria you have here, that extra calculation, you have to keep it. Otherwise, the other calculations are similar to what you have done in shear force. Right? Next, we will take up that last one. So this you can take it here, after this. Next, you place the extreme, right wheel load at C, and use and calculate the average load on right and left span. Treating, in bracket you can say, treating the load on the section belonging to right side. That's very important. Right? Whatever the load which is there at the section, that you treat it to be on the right side. So next. So that means you prepare a table like this. Load on left side. Average load, I will say. Average load on left side. Average load on right side. Then you say remarks. WR. So first trial 1, that is this. You have to place that extreme right on that. That's what I have told. Then next place, the extreme right will load at C. So that means that is right side. W4 by N. Correct? Huh?
Yes, sir.
Then here this will be W1 plus W2 plus W3 divided by, this is B, sorry, this is A. Average load on left side and average load on right side. So you remarks, you just say WL greater than W or less than W or same. To say either or vice versa. Next, you go for trial 2. So trial 2, it will be W1 plus W2 divided by A. Here it will be W3 plus W4 divided by B. You check this. Right? If it changes its sign, then you can say at that particular point, that is the previous trial, will give you the critical loading case, critical position of the load to get maximum. Suppose I will say here WL greater than WR, say, in this case, right? Then trial 1, then therefore here it changes its sign, so therefore trial 1 gives position of B loads to get maximum bending moment. That's it. So at that particular position, you place the B load like that, right? That is at C. Here W4 is that as per this. Then you use ILD. So this is the maximum ordinate, which is nothing but AB by N, where this is A, this is B, AB by N, you get the other ordinate, calculate the maximum bending moment. That is W4 into this, that value you calculate. This is when you place the extreme load and try and do the calculation. Next, you do this. Allow wheel load to move from right to left. Left to right you have allow, right to left you allow. Repeat this process. Right? For the first position, you find out average load on left and right. Next you allow next load to move. Again find the average. You check whether this average load on left is same thing, and on right side whether whatever remarks column, just check whether same kind of thing is happening or not. If it changes, then you can just say the previous trial is the critical, and that particular previous trial position you write it. Take the standard IND for maximum bending moment and work out.
This BMB is for only critical condition.
Critical condition only, this you have to do, not all. Right? Whereas in the previous case, shear force, for each case you were doing the calculation. Here don't do that. For each case, only in table you do that. Then one by one you allow that. That is the criteria. You satisfy the criteria one by one and work out only for the critical position only you compute the bending moment. That's only one calculation. So that will be the maximum. That is when you allow from left to right, right to left. Both you have to do. So whichever case is maximum bending moment, you take it. That is the maximum bending. That's all the exercise. Maximum shear force, maximum bending moment, maximum reaction either left and right support, as well as absolute maximum shear. All these I have completed. Only I have left with now how to find absolute maximum bending moment. So if I say that, then this particular thing, analysis of these for kind of concentrated loads will be worked. So you can take any numerical example, right, and finish that. So we will take up the last case, that is to find absolute maximum bending moment in the beam. That is 4, to find absolute maximum bending moment. Absolute maximum bending moment. It is not just maximum bending moment, right? So this absolute maximum bending moment, it depends upon two things. One is the center of the span. In the previous video case, we are taking the point in the beam, center point in the beam is always gives you the maximum bending moment, that place in the wheel symmetrically about that. Here we don't do it, so we find the CG of the wheel load, right? And also we select the two wheel loads very close to that CG line, right? If at all you have a maximum wheel load very close to that CG, that only one load you can take it. Otherwise, better to take both the loads which are closer to the CG load, CG line, and you place that CG line at one of the wheel loads, right, symmetrically about the center point, right, same distance from center point, and you calculate the bending moment under the load, not at any position point on the beam, under that particular load, that is either W3 or W4. So we can say to get, this is the criteria. First I will give you the criteria. The criteria, you remember, you apply that particular criteria and place the wheel load, then use standard yearly workout absolute maximum. Only criteria applied is very, very important. So you say to get absolute maximum bending moment, absolute maximum bending moment, we have to examine two cases. So first case, so the wheel load, first we have to, in the first case, we have to place the left side, we have to place the nearest, left wheel load, nearest left wheel load, nearest left wheel load close to CG of wheel loads, right here, W3. This is the CG of wheel loads I have told. This is the nearest left wheel load, that is W3. This is very important. You have to find CG of wheel load first, that I give the calculation. Then you identify left hand, close left hand, right side wheel load. You select that CG of that close to left side CG wheel load, close to CG which is on the left side, that is W3. You have to place that nearest left wheel load at a distance, x, which is equal to L by 2 minus EL by 2 from left end of B. So this immediately takes care of that the thing has to be placed symmetrically about the central line. L by 2 means it is center of this span. EL by 2 means this will come at half of EL by 2. And another, this thing, half will be CG of the wheel load. That CG of the wheel load and that wheel load, very close to that, it will has to be placed symmetrically above central span. That particular thing will satisfy. So straight away this has given. So that's why in the beginning itself I told, given a train of concentrated loads, you have to find the CG of the wheel load and you have to locate the left and right closest wheels and calculate their value of eccentricities from the CG, that is EL, left side wheel load, this as ER. Then for calculating the position here now, that EL by 2 you calculate it, L by 2 minus EL by 2, take it if it is on the left side. So at that position, at that distance from left hand, you place that wheel load W3 first. Then all other wheel loads, you can arrange it. Then take the standard ELD for getting maximum bending moment under that load, not any point. Under that load, whatever point is there, that distance x is known, that is your A. Other distance you can work out, that AB by L you take it, then you work out the ordinate. That's the only change. You have to arrive at that distance here, very close to that. That take you have to sense and work out here. Similarly, for other wheel loads, W4, you keep it from right end at a distance equal to L by 2 minus ER by 2 for that position. First, you keep that wheel load, then you arrange all other wheel loads. Then you take the standard ILD, work out. Yeah. Out of these two, whichever gives you maximum, that is the absolute maximum. Otherwise, sometimes whichever is closer and whichever is heavier out of these two, that you can take it. But suppose if both of them may be of same magnitude, you don't know. Or this may be shorter magnitude, this may be larger magnitude, smaller magnitude, larger magnitude, and this is the distance between them will not vary much. The position of the wheel load. In that case also we don't know, we will be at a dilemma. Which load, under which load maximum bending moment occurs. So that is why better you calculate for both the things, work out the maximum. That's all the procedure. I hope I made the things clear. So from left end of the beam and as in figure. So that is a very, very important sketch you have to make. So this W3, you have to place it at X. That X value we have worked out. That is, don't bother about that center and all those things now. So this you place it and then you place other wheel loads. W2, W1 will be here, W4 will automatically come here. W2, W1. For this position, right, you know this is X, this will be L minus X. So you work out the ordinate here, the maximum ordinate under this load, not point and the beam, it is under that load. And this ordinate is nothing but X into L minus X divided by L. So this is X into L minus X divided by L. Then you work out corresponding to this. This divided by this distance. You keep that value, that you multiply by this distance. You will get the ordinate here. Then again, that value you multiply by this ordinate, you will get this. Like that, this also you can work out. Then find out M for this. So this is ILD for M under W3. That is very important. Not any point. Not at C. It is not at center of span also. It is at W3. So this you have to be very, very careful. Then you repeat that case 2. work then using the as in figure for this position. For this position using IND calculate M. Next, case 2, right? Case 2, place the right side, place the nearest right side wheel load. Nearest right side wheel load close to CG. Right? At a distance x1 equals L by 2 minus ER by 2 from right end B. So place the next right side wheel load. So here it is W4. That you place it from right end. That's very important because it is right side. From right end, you take that here instead of left hand, you take it from that right end, as in figure. Right hand B as in figure. So that figure, this will be your x1, this is W4.
W4. Yes.
That's very important. W4. So here it will be x1 into L minus x1 divided by L. So you can place all of them wheel loads here, all of them wheel loads will come like that. Suppose you have somewhere here CG, then 2 will come on the other side. That you have to be careful. Here in this sketch, only one wheel load is there, nothing on the right side. Other wheel loads can arrange it during the process, some may go out. Don't be afraid, don't bother. Whatever you arrange simply for that position. You calculate, repeat it. So again calculate them. Out of these two cases, whichever gives you the maximum value for them, we call that as absolute maximum width. So this is the procedure for a train of concentrated load rolling on a beam, how to calculate the critical stress resultants. That is maximum reaction at support, maximum bending moment and shear force at any section, and absolute shear force in bending. Now we can take up an example and repeat this process, do the calculation. I'll set you a question and you try to work it, because immediately if you work it, then you will never forget the things, otherwise you will forget the things. So now since you are fresh about the things, so it will be easy. Once if you work a problem, then everything will go and settle in your mind. Otherwise, you will forget it. If you leave some gap, time gap, then you will forget everything, all these criteria. You say, fine. I will take only this last one. Fine. Give everything. I will work out on my own. Only the last one, absolute maximum bending moment. I will give you, work it here, and you can work the other one. Find the maximum shear force. Find, I will say from maximum shear force, I will say absolute maximum shear force. When I say absolute maximum shear force, you have to find maximum RA and RB. Out of that maximum, you have to take it. There is no way. So absolute maximum shear force and bending moment. Absolute maximum bending moment for the beam subjected to as is shown in figure. As shown in figure. Also find maximum bending moment at a section 8 meter from left hand. So it is same maximum bending moment and shear also it can improve. So for a beam, 20 meter span. So I will take a beam, L is 20 meters and you have to find out at a section 8 meters from left hand when it is subjected to a train of concentrated loads, moving concentrated loads like this. So this 3 meters, this is 2 meters, 4 meters. So this we can take 200 kilonewtons, 70 kilonewtons, 100 kilonewtons, and 50 kilonewtons. So this is 1, 2, 3, 4. So either moving from left to right or right. For this particular kind of concentrated loads, rolling on this particular beam, evaluate absolute maximum shear force, bend absolute maximum bending moment, and bending moment at section C. That's using this procedure. So if you work this problem, then everything will be clear, whatever is there. So generally they will ask only either this variety of problem or UDL, either shorter span of some length or longer span. For that very simple, there is nothing much here. Only this, we have number of criteria which you have to remember. Only these two varieties of problem you will get in this unit 2, nothing other than that. Rolling loads and evaluation of critical stresses in the beam. So let us try to finish it, at least one. Let's do it. So first we will take up maximum shear force. Right? So first you take preliminary calculations. Preliminary calculations. So what are the preliminary calculations you have to make? You have to find the CG of the wheel loads, $200, this is 70, this is 100, 50. Correct? And this is 3 meter, 2 meter, 4 meter. This is 1, 2, 3, 4. Right? So, taking moment of wheel loads about 1. About that 1 is that x bar, that is distance of CG of the wheel load from 1 we get x bar is equal to 100 into 3 plus 17 into 5 plus 200 into 9 divided by the sum of the wheel loads as 50 plus 100 plus 70 plus 200. So this is nothing but 300, 350 plus 1800 divided by, this is 0, 7, 2, 420 is the total load. So this is nothing but 0, 5, 2450 divided by 420 or 245 divided by 42. This 5.8.
8.
Huh?
5.8.
Yes. Same. So that means this CG of wheel load is 3 to here it is. This is your CG of wheel loads. So which is from here it is
5.8.
5.8 meters. So the other two wheel loads which are closer to that EL and ER, you can work out here itself. That is very useful. So this is EL, ER. That's what we have told. EL is nothing but. So this is 5.8 minus 5. Correct? So that is 5.8 minus 5, that is 0.8. And ER is nothing but, so this is your 4 meters minus, this
So
is
9 minus
5.8. So
9
this, of course, if you take that entire beam, so it is 20 meters, 20 minus 5.8, right? 20 minus 5.8, if you take it, that is 14.2. This wheel load is from right end is at a distance 14.2 from that, and the position of CG. It is from the CG
9
position.
minus 5.8.
From this is from 5.8 actually from A, no?
Yes, sir, from first load.
This is, of course, it is okay, 5.8. So I will take it like this now. So from here, the CG of wheel load, so I will take it. So it is 5.8 from here. So then from here, if I take it, so that location, so from a section, see we have,
8
this is 8 meters. So that we have to calculate actually. So this wheel load, W3 is 70 kilonewtons. So the 70 kilonewton wheel load is at a distance equal to 0.8 meters. So therefore, this 0.8 plus 5, it is 5.8. And this, is it right?
So that's 9 minus 5.8.
That of course, EL and ER only we will calculate it.
Yes, sir.
With beam position, we will work out afterwards.
CG.
Because position, you know, L by 2
Yes,
point
we have to match the
only
CG.
from X and X1. There we will calculate L by 2 minus EL, ER. There we will get with respect to N points. Here we determine only EL and
Yeah,
ER.
9 minus
ER is
5.8.
equal to 4 minus
9 minus
point,
9 minus 3.
4 minus this EL,
Okay, sir. Sir.
0.8.
So we have
That is
3.2.
3.2 meters.
Or we can take full entire length of the loading minus
From
5.
that also you can work out either way.
Yes.
So this is the first calculation you have to make, because all these EL, ER, X bar location, this X bar is from the first wheel load. We are taking moment about that first wheel load only we are taking. This preliminary calculation you have to make it. So that is your first step. Then second step, to find absolute shear force. That is this absolute maximum shear force. This is absolute maximum shear force. For this, I have to first take to find, in these two cases, to find maximum RA. First you find maximum RA and RB, whichever gives you maximum value, that is absolute maximum shear force. So the first wheel load, in order to get maximum RA, I have to place the first 50 kilonewton wheel load here, next 100, next 70, next 200. This need not be to the scale, don't bother about that. 3 meters, 2 meters, 4 meters. So then you have to use, this is the first position, trial 1. So position of the loads to be as in figure A. This is we call it a figure A. So then the IND for this position is this. This is 1. So we have to find out what is this, what is this, what is this. So this length is 20 meters, right? So if you go a length of 20 meters, the ordinate is 1. 1 by 20 means it is 0.05. Now, this is your y1. Correct? Then y2 have to work out. What is this distance? It is nothing but 20 minus 3. 20 minus 3 is 17. 17 into 0.05. That is 0.85.
0.85.
Okay? That is 0.85. Straight away you will get it. This is 1, 2, 3, 4. Then what is this ordinate? It is 20 minus 5. That is 15. 15 into 0.05. It is 0.75. Right?
Yes.
I am doing very fast calculation like this. You will also do as per another method. Otherwise, work out the distance. Then what is this ordinate? This is 20 minus 3 plus 2 plus 4. That is 9. 20 minus 9 is 11. 11 into 0.05, it is 0.55. This is 0.55. So this is your IND for RA for trial 1. So for this position, work out RA as in figure J. For this position using IND for RA, we get RA equals that 50 into 1, right, plus 100 into 0.85, 100 into 0.85 plus 70 into 0.75 into 0.75 plus 200 into 0.55. So this you can conclude you get trial 1 shear force.
297.5.
I hope it's correct, 290?
7.5.
Okay. So this is what RA for trial 1. Next, trial 2. Trial 2. So next, move the next B to position A as in figure B. So I will draw another figure. This is the only calculation you have to make, nothing other than that. So next wheel load means it is 100. Next it will be 70. Next 200. So this is 4 meter, 2 meter. So A, B. You have this wheel load 2, 3, 4. One will go out. Next, as in figure B. That's what I have told. As in figure B. This is the figure B. Again, similar to this, for this figure, using IND, right, like this. So you work out the ordinates here and here. As usual, this is 21, that is 0.05 we got. So this distance is 20 minus 2, 18. 18 into 0.05, so this is 0.9. This is 1. Then this will be 6. 20 minus 6, 14. 14 into 0.05, that is 0.7. So this is IND that you have to do correctly, the calculation of ordinates. Nothing other than that in this. It is simple arithmetic computation. So this is IND for RA. So for, as in figure, so for this position, for this trial 2, I have written here trial 2, for this position RA is this 100 into 1 plus 70 into 0.9, that is 63. Then 200 into 70 into 0.9, 70, that's 63. 200 into 0.7, 140. 140. So this value
303.
will be 303. More than that. So one more trial. I think that trial will give you maximum. Because we are allowing this, moving like this. So you can go from other end also repeat it. Then next trial 3. Trial 3. So move the next load to position A. Position A as in figure C. So that is, each time you better draw a sketch. So it will be now 70, the third wheel load will come. This is the fourth wheel load, 200, 4 meters. So this is figure C. For this position, you have only 2 ordinates. One is this, another is this. This is 1. So this is 16. 16 into 0.05. 0.8. So you get it. So therefore, this is IND, right? Therefore, for this position, RA will be 70 into 1, 70 plus 200 into 0.8, 160, that is 230.
230.
Right? So, it is less than this. Therefore, maximum RA is 303. So, maximum RA is 303. You have found out one. Same thing you repeat for RB. So you place the wheel load, the extreme right wheel load there, allow 1 by 1, do the calculation, again work out maximum. Out of these two, whichever is maximum, that will be absolute maximum shear force. So I think we will continue that absolute maximum minimum. I want to work the same example. Maybe in the next class I will finish it. So